So welcome you all students to this class of work, energy and power. So this lesson is actually a very exciting lesson in physics because this simplifies very complicated Newton's laws. So this is, I usually consider this as a shortcut for Newton's laws. So this was a wonderful thought by human beings. And there is no history which is telling us that who invented this concept. I think it should have been a very group of people who think very wisely should have formulated this idea of work, energy, power. Always, I usually used to think that physics is completely made up of two concepts. One is force, the other one is energy. All the lessons will fit into these two concepts. Anywhere you see in 11th standard and 12th standard, there is a lot of force and energies, fields and potentials, which is an integral part of force and energy. So the entire physics can be understood if you can understand about force and energy. So like Newton's laws, where you study about force, this lesson is also going to be very, very interesting and very, very important to do many problems till the end of your science career, at least your 12th standard, or when you get into engineering also, this concepts will be handy for you. So this is a very, very important lesson. So first I'm going to tell you the concept of work. And I'm going to do some problems, basic problems of work, and then I'll move on to something called as work energy theory. Work. So I'll start from where we left, something what we know already. So what we know already is, if you have a particle here, you have to, few of them be interactive at least. If I have a particle here, say I have a particle here, say I have a particle here. And if I'm going to apply a force here, what will this force do to this mass, to this particle? What will this force do to this particle?
Sir, provide acceleration.
Yeah, it changes its velocity. Am I correct?
Yes, sir.
It accelerates or it changes its velocity. It changes its velocity. If after some time, its velocity here is v1 and the velocity here is v2. If I call the velocity here is v1, and after some time, if it has a velocity v2, sorry. If it has a velocity v2, then I can formulate a relationship between this one. If I call this distance is d, this distance is d, then I can write a relation between this v1 and v2. I can write v2 squared is equal to, from our kinematic equations, v1 squared plus 2 times a into d. So now I can even write this one as v2 squared is equal to v1 squared plus acceleration is force by mass, 2 times force divided by mass into d. So if I want to find the different change in this velocity, because this force is changing the velocity, if I'm interested to find the change in velocity, I'll bring this v1 squared here, v2 squared minus v1 squared is equal to 2 by m times f into d. So if I bring this 2 and m to the other side, I'll get m by 2 v2 squared minus m by 2 v1 squared is equal to force into displacement. So this equation gives me some kind of relationship between the velocity changes with respect to distance. The velocity changes with respect to the distance. So this equation gives me, if I'm going to call this terms by a name, we call it as a kinetic energy. I call this as kinetic energy 2 minus kinetic energy 1. That is, this is final kinetic energy, this is the initial kinetic. This is equal to F vector dot D vector. Vector wise, if you write it as a vector wise, F vector dot D vector. So this equation is very important. This term, F vector dot D vector, we define this term as work. We define in physics this is work. Here, this is somewhat an easy term. This is the force. Directly you can tell this is the force. If this is the force, a lot of forces we have done already. So this one is very, very important. And calculation of this one is, it's not very easy, but you need to be very careful in applying what is the distance. This is the displacement of the, this is not just the displacement. This is the displacement of the point of application of the force. Many of the textbooks and even many teachers doesn't emphasize on this one, but this becomes a very, very important point in solving problems in mains and advanced and even in NEET. This is the displacement of the point of application of the point of application of the force. Where you apply the force, the point you move out in the point you displace point of application of the force. This is very important. Concentrate of the force. Of this force. Suppose if I ask a question here, a man is walking on a floor. A man is walking on a floor. Is moving in this direction. When the man presses against the floor, the friction will act in this direction. In this direction, the friction will act in this direction. Because you are pressing backward, then only you can move forward. The velocity of the man will change. Definitely, the velocity of the man will change. The friction force will accelerate the man. Can anyone tell me what will be the work done? The man is getting displaced in this direction. Work done, since this is a dot product, in vector you know that work done could be it could be positive, it could be negative, or it could be zero. Can anyone tell me what is the work done in this case?
Negative work done, sir.
Why?
Opposite to the frictional force is the displacement.
Which is the opposite?
Angle is 180 degrees.
The friction
Sir,
force.
angle is
The friction is in this direction. The man is also moving in this direction. The friction will be acting along the floor only. Yeah, tell me.
sir.
Sir, both force and displacement are in same
Positive means
direction.
what? Positive means what? What is F dot D means? In vectors, you call it as FD cos theta, no? FD cos theta. F into D into cos theta. So this is to separate the terms. This is not a dot product. This is F into D into cos theta. If theta is less than 90 degree, this term will become positive. If theta is greater than 90 degree, this term will become negative. If theta is 90 degree, this term will become 0. If theta is 0 degree, this term will become just F into tau. So in this case, if theta should be positive, means theta should be less than 90 degree. Negative means theta should be greater than
90.
90 degree. 0 means theta should be equal to 90. So in this case, tell me what is the work done? I want answer from everyone, all the 32 students who are there.
Greater than 90. Sir.
So today many students are attending. 44 students are attending. Give some answer. Is this positive, negative, or zero in this case?
Positive.
Positive. Positive. So 2 positive I got. Yes, many answers.
Positive, sir.
Positive. You can chat. You can chat. Chat window is open. Rahul has given positive. Positive. Yes, is positive. Greater than 90, so positive. Rakesh is given positive. Karanidhi positive, 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 positive. So a lot of positive answers are coming, but that is not the correct answer. Unfortunately, that is not the correct answer. Everyone are giving wrong answers. Actually, work done here is zero. Because this is the point of application. Next time, he steps out of the floor and then he keeps his leg here. The point of application is on the floor. The floor is not moving. Where he applies the force? He applies the force on this point. This is the point of application of the force. So friction force is acting on that point only, on the floor only. So that point is actually not moving. When he raises his leg, it is not in contact and friction force will not even be there. So the answer in this case is zero actually. So most of the cases, people think that the work done here is positive, but it is not positive. Then you can ask me a question, then who is doing the work and how the man moves? The man is not, the friction may be the reason for man moving, but that doesn't make the man to move. That gives us kind of support. The man is moving by his muscle strength. The man is moving by his muscle strength. He is not moving due to friction. The muscle strength cannot be drawn in a FBD diagram. I cannot draw the muscle strength in this FBD diagram. So in this case, work done is zero in this case. Now you will answer the next question. See, if I'm going to give you this kind of question, first let us not try to mug up all the formulas and try to answer this. If this plank is lying on a smooth surface, let us understand the concept to the core. Now, if the man is moving in this direction, friction will be acting in this direction. And this plank is lying on a smooth floor. In this case, what is the work done? Whether will it be positive, negative, or zero? See, in this case, this point will move backward, no? In this case, the man is walking means the friction will be acting in this direction, but the displacement will be, this plank is going to move in this direction, no? Because this is lying on a smooth surface. When you put some smooth, when you put some polythene cover on the floor, and if you try to walk on that, the polythene cover will go back, no? So the plank is lying on a smooth surface, so there is no friction acting. So when you try to push it, what will happen to this point of application? That will go back. The point of application will go back. So in this case, it is negative. So do you understand this point? Now, do you understand this point? Displacement of the point of application of the force. That is very important. Another example I can take. If there is a huge mass, and if there is a spring, a man pulls the spring. A man pulls the spring. The spring will expand, but this block is not moving. This block is very huge, and this is lying on some horizontal rough surface. This is lying on a rough surface. Or else the block will move even if this is a smooth surface, you cannot avoid even a very feeble amount of force will make the object to move, however massive the block is. Only if it is lying on a rough surface only, it may not move. Now my question is, he's pulling the spring is stretching out, but this block is not moving. What is the work done by the man on this spring? Will it be positive or negative? What is the work done by the spring on the block? Will it be positive, negative, or zero? In this case, will it be positive, negative, or zero?
So spring on the block is 0, sir.
Spring on the block is 0 because this point is not moving. This is the point of contact. This is the point of application of the force. Here only the spring is trying to pull. In this case, it is positive, no?
Positive.
Because he pulls this one. The force is also in this direction. What is the work done by the spring on the man? That will be negative. Because the spring force will be in this direction. And the point of application is moving in the opposite direction. So spring is doing a negative work on the man. But the man is doing a positive work on this. And the spring is doing no work on this block because the block is not moving. Because the block is not moving. Is it clear, the point? I'm emphasizing on this point because most of the students do mistake in this point. And I have seen many teachers also not emphasizing on this point. Many teachers also giving the same answer what you are giving. So now, is it very clear for everyone, at least here in this room?
Yes, sir.
So tell me, what work done by the spring on the man? Is it positive or negative or 0?
Negative.
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 Very good, super. What is the work done by the man on the spring?
Positive, sir.
What is the work done by
Positive,
the
sir.
spring on the block?
0.
Zero.
Zero, sir.
So I think it should be clear. I have given a very good 3 examples where there is an emphasis. I emphasize on this point. I have put some light on this point, the displacement of the point of application of the force. So this is actually very complicated and this is not easy to calculate. You should be very careful since the man moving. Here, who is doing work? In this case, the velocity of the man is changing. So someone is doing work here. Who is changing? Who is doing the work here? It is the muscle of the man. Work done by the muscle of the man is that. That is only changing the velocity of the man. Did you understand? So I've given very good examples to understand this work done. Work done is equal to, in physics, this is what work done is being calculated. So now I'll do some examples for you where you understand work done in this case also. Listen. Suppose there is a lift. Listen to this equation. Sorry. Listen to this equation. This equation tells you this force. If you ask me what happens if more than one force, 19 forces are acting on this on this block. Never mind, you add all the forces. Vectorially, you add all the forces. And then dot product by displacement. So this force is actually work done by all the forces on the system. This force is the work done by all the forces on the system. In this case, at least. In this equation. This need not be the work done. This need not be the force acting on all the forces acting on the system. This can be a single force in this case. Work done by a single force. In this case, you are considering the entire system. The kinetic energy of the system changes. And the kinetic energy, the change in kinetic energy of the system is equal to work done by all the forces here. In this case, F is all forces on the system. That is also one important point. In this case, F is all forces on the system. All the forces on the system. Vector sum of all the forces on the system. All the forces on the system. This need not be like that. This need not be all the forces on the system. This could be a single force. This could be only friction force. There are two forces. There are two work done by two of them. Friction is doing 0 work, but the muscle of the man is doing. Here, friction is doing a negative work. Muscle of the man is doing some work. So there are two forces here acting on the man. But on the whole system, only one work is done. That is muscle work only is done on the whole system because friction becomes the internal. What you observe from these two cases is listen. This point of application here, if you are going to consider, I'm not going to move on to the next page. I have some points to tell you now. If there is a block here, and the man is walking. Now for man, I already drawn the free body diagram. For the block, the friction force will be in this direction. No? The friction force in this direction and the same displacement in this direction. No? So what is the work done by this friction? It will be negative. Negative. It will be negative. And that will be equal to minus F into D. No? Friction force into work done by the friction in this case. Work done by the friction into D. D is the distance moved by this point of application. In this case also, work done will be work done by friction. This is, I will write it properly. I'll write it properly. What is this? This is work done. Everyone listen. This is the work done. Work done by the friction on man. This is the work done by the friction on block. That will be positive here. Fr into D, no? Fr into D. Fr into D. So what will be the total work done by the static friction? The total work done, this is F minus Fr into D, this is plus Fr into D. So this point is also important. This is also very, very important. The total work done, I'm not in a hurry to complete anything here. I want to make sure that this class goes slowly and you understand all the concepts clearly. And then we can go and fly. The work done by static friction is always zero. Static friction, static, the object is the point of application, static friction. The one object is not moving on the other, static friction. The objects may move, but there is no relative motion. Static friction is equal to zero. That is work done by, in this case, work done by friction on man plus work done by friction on block should be equal to zero. So now let me get your responses. Do you all understand?
Sir, how is the work done by static friction on block positive, sir?
Because both displacement and friction force in this direction. Friction force on the man will be in forward direction. That means friction force on the block will be in the back direction. On the foot of the man will be in forward direction. And on the block, it should be in opposite direction. No? Friction forces on the block and the man should be in opposite direction. Because always force comes in pairs. If this is the reaction, this is the action. Or if this is the action, this is the reaction. Any doubts? Further doubts?
Sir, this is with respect to the concept, but with respect to the surface, the friction will be opposite to the motion.
If someone is standing here and saying, listen, if someone is standing here and saying, work done measured by this man is zero. That's a nice question actually. This allows me to tell another concept. If someone is standing here and saying, he will not see any movement of this block, of this point of application. Because when the block moves backward, he will also move backward. So the distance between this point and this man is not going to change at all. So work done as seen by this man is zero in this case. I'm measuring the work done as seen by a person standing outside. For him only, block is moving in this direction. Block is moving in this direction, and the foot of the point of application of the foot is also moving back. In this case, the foot will move backward because this is slipping down. This is slipping down. You will move backward. It will move backward. That is why it is difficult to walk on this kind of system. So for this man, it is the work done. That is what we have calculated here. For this man, work done is zero for this man. Understood?
Yes, sir.
For this person, this point is not at all moving with respect to him. You will calculate the zero displacement. Yes, ask me.
No, so the frictional force, so So the frictional force between the block and the floor, sir, which direction, sir?
Block and the floor, I given it as a smooth surface.
Okay, so no, okay, sir.
If
Understood.
the block is moving on a rough surface, that is not no more. It is not a static friction. I am telling you, work done by static friction only is zero. Any doubts? Anyone else? Anyone else? Any doubt? So I'll move forward. Okay, I'm here now. So this is also one point, no? Friction force work done is not only these points. I'll add up 1 point more. Work done is also depends on the observer, no? Work done measured differently by different observer. All the work done is measured. Very good point. This one is measured differently by different observer. Differently by different observer. This person measures differently. This person measures different. For this person, work done is not equal to zero. For this person, work done is not equal to zero. For this person, work done is not equal to zero. For this person, work done is equal to zero. I'll put this person going to far away. And then if this person is standing here, if this person is standing here, he calculates work done is not equal to zero. Is it clear for everyone?
Yes, sir.
Yes, sir.
See, how many points are arising because of the doubt arising by you? That is the importance of you asking doubts. I might, even if I miss some points, your doubts will force me to tell you those points. I would have missed that point. Thanks, Mark. So this is work done by friction on the block, and this is plus. I'll put a plus sign here. That gives a nice feeling here. Positive work done. We are talking only about the sign of the work done here. This is negative, and we have come across this very important. I'll put colors for this. This is a very important point. Put many colors. Make it colorful. This is a nice point. I'll also put a nice color for this one. So now listen. Yes, I think I can move on to the next page. So now I was talking about a lift here. This is a nice problem for you to understand friction furthermore. Sorry, work done furthermore. If a person is, if a block is placed here, not person, if a block is placed here, whose mass is m, and this one is moving upward with a constant velocity v. Now, I know the mg is acting downward, and normal reaction is acting upward. What is the work done by normal reaction on the block? Work done by normal reaction on the block in time t, after time t. In time t. after t seconds. I'm measuring all these quantities. That should be equal to plus normal reaction into Vt, no? Vt is the distance moved. Am I correct? Because the object would have moved upward by distance Vt, no? That will be the distance moved, no? Distance is equal to speed into time. Any doubts?
Sir, but that is not due to the normal reaction, right, sir?
Why you are bothering about it? That is what you have to make your mind set for. The work done, what you are seeing in your normal life is different from the work done that is being explained by that you understand in physics. That is, both are completely different. Both are completely different. So your job is to work done by normal force and abundant. Your job is to find the normal force and multiply the with the normal force is applying here means this point எவ்வளவு move ஆயிருக்குன்றது நீ apply பண்ணலாம். That's it. Understood? If the normal force is acting on this point எவ்வளவு move ஆயிருக்குன்றது apply. What is the work done by? Your question will be naturally answered. Wait and see. Work done by gravity on the block. What will be the work done by the gravity on the block? Mg is acting downward, but the object is moving upward.
Negative.
Minus mg into Vt.
VT.
Yes, sir.
This acceleration is zero, no? No, guys. This acceleration is zero. Am I correct?
Yes, sir.
If I write Newton's laws, I'll get n is equal to mg, no? I'll get n is equal to mg. Am I correct?
Yes, sir.
So what will happen to work done by gravity on the block? That is also going to be equal to what is going to be this one? mgvt, no?
Yes, sir. Plus mgvt.
Plus mgvt. So what is the work done by normal force in this case? The object is not moving in this case. Sorry, the object is not changing its velocity. The velocity, it's a constant velocity. See, now you will understand very clearly what I mean to say. So here you get work done by normal force on the block plus work done by gravity on the block. This add together to zero. Now see the previous equation. What I told you. Work done by all the forces should be change in kinetic energy. No? Work done by all the forces is equal to change in kinetic energy. In this example, there is no change in kinetic energy because the acceleration is zero. The lift is going to move with the same velocity. So after some time t also there's going to be v only. So the change in kinetic energy in this case is zero. So we, according to the previous equation, we should have got work done by all the forces. There are only two forces acting on this block. One is the normal reaction, the other one is the gravitational force. So work done by all the forces acting on the block sums up to zero here. Is it nice for you now? Do you understand now?
Yes, sir. Sir, is that modulus, sir?
Huh?
Is that modulus?
No, simply I just want to separate it. Okay, I'll erase it. What is that? What happened? I'll erase it. No problem. That's not modulus. Simply I thought of separating that. It cannot be modulus because if it is modulus means it cannot be zero. See here. Now listen to this example. There is a lift here. This is accelerated. Initially, let the velocity be v1. Initially, let the velocity be v1. And this one is accelerated. acceleration. This is acceleration. Initial velocity is v1. And that is the same block here. I change the colors. There is a block here of mass here. And again, this is mg. Sorry, this is normal reaction. And this is mg. And this is here. Now, what is the work done by normal reaction in time t? In time t, what is the distance traveled? Ilana, I'll consider the initial velocity 0.
Sure.
Initial velocity. I'll consider the initial velocity 0. U 0 here. From 0, it is accelerating. So not what now? What is the yes? Half at square, no?
Half 80 square.
In time t. Now, what will be the work done by normal reaction?
Sir, n into half 80 square, sir.
Work done by normal reaction on the block. N into n into
Into half mv square.
half at square.
80 square.
Here there is a change in velocity, no? What is the work done by gravity? Do we expect some of these two will become 0 here? No, it cannot be 0. In that case, there is no change in velocity. If there is a change in kinetic energy, the work done by all the forces cannot be equal to 0. Here there is going to be a change in kinetic energy because initially it was at 0 velocity and then it is going to acquire some velocity here. So what will be the work done by gravity? It's going to be mg into half at square. Am I correct?
Sir, minus mg.
Yes. Minus mg into half at square. Now, listen everyone. Now, what will be the normal reaction here? Normal reaction in this case will not be equal to mg. If I write the our Newton's law equation, this is accelerating. This is accelerating. So net force should be equal to mass into acceleration. This is capital A. Excuse me. So in this case, n minus mg should be equal to ma, or n is equal to m
G plus A.
So here, this term is not going to be simply mg into half at square. This term is going to be mg into half at square plus ma into half at square. Understood?
Yes, sir.
This is the n is not going to be equal to mg in this case. N is going to be mg into plus a. So when you add these two things, this and this will get cancelled, but this remains. So work done by, in this case, work done by normal reaction on block plus work done by gravity on block should be equal to half mv square, no? What is V is equal to? What should be V is equal to? 280, yeah? V squared is equal to U squared plus 2AS, no? U is 0, no? What should be V squared here? AS, no? What should be V? Come on, what should be V squared?
2 AS.
What is S? S is here. Substitute it. What do you get?
A squared T squared. Half M A squared T squared.
What is there above? What is the work done? When you add these two, what do you get? When you add work done by normal reaction and plus work done by gravity, what do you get? Half M A squared T squared. What do you get here?
Same. Yes, sir.
Same you get. Is this not the beauty here? This makes us very happy, no? We have calculated by two different methods. This is by the previous equation. This one we have calculated, we have found and we have added it. So it is more convincing here. No? Do you all understand?
Yes, sir.
Yes,
Everyone,
sir.
others, 42 of them are there in the class. 42 of them are there in the class. So this is the highest we have reached. I have stressed upon a message. But all the 42 students who are there attending here, be attentive to the class, be punctual to the class, don't miss the class. Try to attend the class. Then you will not feel physics no more a tougher subject after 6 months or something. Physics is the easiest subject because this is a natural subject. This is a very easy subject. One reason is I told you there is only two lessons. One is force, the other one is energy. If you learn force and energy properly, your Newton's law, that is why I'm taking a lot of time to explain you what is energy and what is work and what is force and all the things. If you understand these two things, the entire physics will fall into this. So don't miss the classes. Don't miss the classes. Okay. So you would have understood what has happened till now. So this is all about work. Did you understand? This is all about work, calculating work by the idea of point of application. Now I'm going to move on to the one equation which we already saw. I'm going to go deeper into that equation. We saw this equation already. Listen, we saw this equation. K2 minus K1 is equal to F into the displacement. Maybe I'll put a vector. Here, the condition is force should be a constant. Force is constant. Or you get confused, what force should we should I? If force is a variable, what to do? I'll write this one in another beautiful form like this. Del K is equal to work done by all the forces. Change in kinetic energy is equal to work done by all forces. This sentence is famously known as work energy theorem. This sentence is famously known as work energy theorem. If you can apply work energy theorem properly, you can solve any problem in this lesson at least. This is famously known as work energy theorem. I will call it as WET. Work energy theorem. I'm going to call this one as WET in future. So this is famously known as work energy theorem. Now I will come back to this equation. If force is a variable, what should we do? If force is a variable. If force is a variable. If force is a variable, suppose I'll draw the force here. I'll draw a graph between force and displacement. This is force. This is displacement. Suppose the force is a variable like this. This variable work. So I'll put a smooth curve. Like this. Say force is a variable. This is not a sine curve or something. This is just a curve. So if I want to find, actually from this equation I can tell you the work done by any force is nothing but force into displacement means what? It is the area under force displacement. I can also define like this. This is area under. This is also very important. Area under force displacement. Not distance, displacement, strictly displacement. Area under force displacement. For example, if you have a force and displacement, if I have a line length, say F is equal to some kx. F is equal to kx. This is a line here. If I want to find the force from x is equal to 0 to x is equal to 10, say 10, then what should I do is, I should simply find the area of this. What will be the area of this one? F is equal to kx, and I can put some number also. I'll take out this one and put some numbers here. I'll put some nice number 2x. We already used this number. F is equal to 2x. If I have F is equal to 2x, then what will be the area of this? Work done is equal to, in this case, work done, what will be work done? Work done will be area under FT graph. What will be the area of this shaded portion? Half base into, what is base? Base is x10. What will be this height? This function is what? F is equal to 2x. So what will be this one? When x is equal to 10, what will happen to this one? This will become 20.
50.
20, no?
Yes, sir.
So work done is equal to 100 joules. I didn't tell about the work done joules. Usually work done is equal to force into displacement. It is Newton meter. But you don't use Newton meter, you call it as joule. Joule, the short form of joule is J. So that is the unit of, this is the unit of work done. So 100 joules. At one place I write 100 joules. You should not write joules and other things. I may not follow exactly the rules which even I would have taught you in units and dimensions, but I never teach units and dimensions, to be real. I would not have taught any one of you here units and dimensions. This is 100 joules. So in this case, if you want to find this is a variable, this is somewhat easier. You know it's a triangle. It's not triangle, and you know the formula for triangle. You have done it easy. But in this case, what the force keeps on changing. In this case also force is a variable only, but this is easier. This is even more easier. No? If you have a graph like this, if you have a graph like this is even more easier. No? If your F is a constant, if your F is a constant, this is D, and this is 10 means. If F is equal to 2 means, what will be this area? 20, no? F is work done will be equal to 20 in this case. What? Do you understand or not? Why you are keeping quiet?
Yes, sir.
Yes. So in this case, what we will do now, we will take a small strip here. I'll draw a very small strip here. And I can consider force to be constant at that small strip, within that small distance dx. This distance I call it as dx. And this length, if it is F means F at that point x. Maybe this is x. This is from here to here, this x. So this is F at that point x. Force at that point x. I'm considering between these two regions, within these 2 points, the force is almost a constant. And I should have taken these 2 lines even more closer. You will not be able to see it. So I have taken it separated. I would have taken as close as possible so that it can be considered as a constant. So in this case, what is the area here? The area is F dx. No? What is work done by that in that strip, for that small distance dx? I call it as dw. What will be the work done here? dw is equal to F into
DX.
Yeah.
Now, if I want to find the entire work from say x is equal to 0 to some point here, then what should I do is I should take similar strips. I should draw a lot of strips here, and I should add all this. So the entire work done, what I should do now, I should do the summation of all this. This is the fx. I should do the summation of all these kind of strips. If I draw as many as strips, small strips possible, and if I find all the areas and add up, I'll get the entire. f dx. Yes. So this, instead of using, in this, this is so continuous that you don't use an summation sign. Instead, you use the work done is equal to integral f dx. Integration sign you are using. Integration f dx. Here, I'm telling you f is a function of x. F is not a constant here. That is what this one tells. I could have written f of x also. F of x. I could have written f of x also. F of x. That would have been even more better. F of x. F is a function of x at this point. Right? If this is x, if this is some other x1 means that f of x. So f of, I'll draw it as fx. I'll make it as f of x. Let me take some time and erase it and make it as f of x. So in this case, if the force is a variable force, then I'll be writing it. So I'm going to rewrite this equation as, if force is a variable, then what will be the change in kinetic energy will be equal to K2 minus K1. Change in kinetic energy is K2 minus K. That is equal to integral f of x, capital F, don't put small x, small f. F of x dx. Small x put in a function of x in the head. Small x dx. You have to integrate this, and if you know basic integration, you can do all this. Did you all understand till this?
Yes, sir.
Yes, sir.
Yes. Now, okay, let us do this integration from here. Let us continue in next class. I'll just send these notes today. Go through these notes today itself once, and then come prepare for the next class. Don't miss out the classes. Those who all attended today's class, to have a good finishing about a most important lesson in physics. Attend the next class also. Next class I will not put lot of messages. I will not do lot of advertisement in WhatsApp. Okay. So everyone make a point that you attend next Thursday's class. So today class is over. See you. Bye bye.
Thank you, sir.
Thank you,
sir.
sir.